So folks, thank you so much for your patience. We're really excited to have you for this session. Earlier this week, we launched Amazon SageMaker Operators for Kubernetes. And this is the first time we're bringing SageMaker and Kubernetes together. So we have a lot of exciting content for you. And let me quickly introduce myself. My name is Aditya Bindal. I am a senior product manager with Amazon Machine Learning. And we have here with us David and Ketan. So why don't we let them introduce themselves? Why don't you go start, David?
Hi, my name is David King. I am a machine learning specialist with Amazon Web Services.
Hi, my name is Ketan. I lead the ML and data infrastructure teams at Lyft.
Okay.
Take it away.
All right, so we're going to get started. Cool, so this is the agenda we're going to be covering in this talk. First, I'd like to explore with you, some of the challenges with building a machine learning platform. And to address those challenges, I'll first talk about Amazon SageMaker, a fully managed machine learning services, and see how it can quickly help you to simplify machine learning. And after that, we'll do a quick review of Kubernetes and its architecture, and follow that with an introduction of the SageMaker operator, and see how that can be used to build a workflow using both Kubernetes and Amazon SageMaker. We'll then have Ketan to share their story on how to use Amazon SageMaker and their flight system to essentially build an end-to-end machine learning workflow using both tools. We'll have that, have a short demo afterwards, and we'll also leave some time for Q&A. Okay? All right, so let's see, your organization has adopted containers and Kubernetes as part of your technology modernization strategy. And in doing so, you have developed competencies in large container management, application deployment, and infrastructure operations. And now your business is looking to enable their business transformations with machine learning. And they hired, a team of data scientists, and they want to give them a machine learning platform so that they can help to achieve the business goal using machine learning. So to build a successful machine learning platform, it's going to require collaborations from your DevOps engineering team and your data scientists. And, but they're going to have different focus area, different expertise, and different limitations. For your DevOps engineers, they will likely want to extend their existing Kubernetes environment to support the machine learning requirements. However, they might find themselves lacking the experience and expertise in building high-performance machine learning infrastructure on Kubernetes. On the other hand, your data scientists are going to want to focus on data science, business outcome, and speed to market. However, they might not have the necessary knowledge on Kubernetes to operate on their own for their experimentation and model training. However, they also don't want to be slowed down by reliances on the DevOps engineering team. So what does it take to build a machine learning platform? Some of us might say, hey, machine learning is all about building models or data science. But in reality, machine learning or model building is only a small portion of your end-to-end production environment. It takes a lot more that goes into to build a production-grade machine learning platform, and it requires seamless collaborations between your data scientists and your DevOps engineers. So in addition to just model building and machine learning, you also need to build infrastructure components for things such as configurations, data collections, infrastructure monitoring, and many other components. And for many organizations, this could present a significant challenges from engineering and operational perspective. So how do you decide on what technology platform to move forward? Do you just want to extend your existing Kubernetes environment and build everything from scratch on your own? But you also need to be prepared to be facing the challenges with the engineering and operational challenges with building such an end-to-end platform. Or you can adopt a fully managed service to get started quickly. How do you balance your existing investment in your Kubernetes and your requirement for speed to market? So is there an opportunity for both? And to answer that question, let's first take a look at Amazon SageMaker, which is a fully managed machine learning service. Now, for those of you who are not familiar with Amazon SageMaker is a fully managed machine learning service that covers the entire machine learning lifecycle. Its modular architecture allows you to use just the component you want to use, such as training or hosting, or just the notebook instances. It has many other features, such as a list of building algorithms to help you speed up your experimentation, and a hyperparameter tuning service to help improve your model. Now, Amazon SageMaker has been built on modern application architecture. It uses container technology extensively. For example, its 17 building algorithms are packaged as Docker images that you can use to train and host your model very, very quickly. There's also a list of managed machine learning containers for you to train your custom model and hosting your custom model for frameworks such as TensorFlow, MXNet, or PyTorch. You also have the option to bring your own containers to train and host your machine learning model. Now, with Amazon SageMaker, there's really no server to manage. You interact with the backend using a high-level machine learning API, and you pay for what you use. It also follows many of the best practices in cloud-native architecture, such as deployment across multiple availability zones. And you have a large range of CPU and GPU-based instances for both your model training and model hosting. And it's also seamlessly integrated with rest of AWS ecosystem and services, such as IAM, VPC, and encryptions. And to help you reduce the cost of running machine learning on AWS, you have the option to use Spot instances for both model training and model hosting. And for GPU-based inferences, you can save up to 75% by using Amazon Elastic Inference. And you can further reduce the cost of your hosting by the multi-model endpoint, which was announced recently, that give you the ability to host multiple models in a single container. So what does this mean to your data science team? How does this relate really to the issue at hand? Well, because it is fully managed, that means you can get started quickly with Amazon SageMaker, with minimal dependencies on your DevOps engineers. Your data scientists can get started with experimentation and model training. And if needed, they also have the option to quickly deploy a real-time endpoint to integrate with downstream systems. Now, because it's modular and API-driven architecture, Amazon SageMaker can be seamlessly integrated into a pre-existing workflow. For example, if you want to build a workflow that has data processing, model training, and model deployment, you can easily use services like AWS Step Function to orchestrate services like AWS Glue, which is a serverless ETL service, and Amazon SageMaker to build out a pipeline that includes data processing, the model training, and the model deployment. So now I have hopefully provided a good overview of the value of Amazon SageMaker and how it can help you to quickly start with machine learning. Next, I'd like to quickly review SageMaker and its architecture. Now, for those of you who are not familiar with Kubernetes, Kubernetes is a popular open source system that for automating the deployment, scaling, and management of your containerized applications. Unlike Amazon SageMaker, which is a purpose-built machine learning system, Kubernetes is a general-purpose container orchestration system that's good for a variety of different applications. So for developers and DevOps engineers, Kubernetes is a powerful tool and familiar tool for them to manage the deployment of containerized applications, creating repeatable pipelines, and orchestrating workloads. From an architectural perspective, Kubernetes consists of two main parts: a master node, also known as the control plane, and a worker nodes. Now, the master node is responsible for running the cluster. It has a programming interface that it can use to interact with the cluster, but it also has many other functionality, such as scheduling the deployment of containerized applications, but also running control loop to monitor the state of a deployed applications. The worker nodes are responsible for running the containers where the application lives. Now, to deploy an application onto container, you simply have to create a YAML specification file that specifies the desired state of your application, and then just apply that YAML file using a command line interface called kubectl. And this is what it looks like. Now, with that, I'm going to hand it over to Aditya to talk about how to use Amazon SageMaker and Kubernetes together to create an end-to-end machine learning workflow.
Thanks, David. So let's take a step back. You're using Kubernetes, and it gives you the standardized way to build and deploy applications, set up repeatable pipelines, and orchestrate workloads. And that flexibility, that control, that standardization that you get with Kubernetes allows you to scale your engineering organization, allows you to scale how many processes and projects you can support, how many applications, and it puts everyone in a similar way of composing all of those jobs and applications. And that's really powerful. But when our customers told us that they're using Kubernetes for machine learning, they encountered some challenges. And chief among them was actually running the machine learning workload. So once you've said, here's how I want to compose my job. I want to train this model. I want to tune the hyperparameters. I want to create an endpoint. Once you do that, beyond orchestration, there's a lot of heavy lifting in actually optimizing and managing the underlying infrastructure. So how do you make sure that you're getting high availability and reliability if you have an endpoint that's serving real-time inference? You also have to optimize the entire software and hardware stack for availability and utilization. So if you're using GPU nodes, you want to make sure that you can get as much processing power and utilization out of them because they tend to be expensive. Now, if you take security as another example, you have NVIDIA libraries, you may have TensorFlow, PyTorch, MXNet, and various other open source software packages. And in one of those low-level libraries that you don't directly use, but it's a dependency for something in your model and model code, you now have to worry about patching that every time there's a security vulnerability. You have to patch the endpoint. You have to update your pipeline. All of this is a lot of heavy lifting. And our customers told us that we want to control everything from Kubernetes. We want to orchestrate. But we don't necessarily want to manage all of the underlying pieces where those machine learning models execute. And we need an easier way in which we can retain that control portability that Kubernetes gives us, but we want to use the benefits that a fully managed service for model training, tuning, and inference gets us. And that's exactly the reason why we built Amazon SageMaker Operators for Kubernetes. So earlier this week, we launched SageMaker Operators. And with these operators, you can now train, tune, and deploy all of your machine learning models in SageMaker from Kubernetes. So let's unpack that and what that means. You have a Kubernetes cluster, and this Kubernetes cluster could be dedicated for machine learning, or it could be part of a broader application cluster that has one piece of it that represents your machine learning workflow. And you can now standardize the way you orchestrate your machine learning workloads and bring in Amazon SageMaker as a new custom resource in your Kubernetes cluster. So it's as if you have all of the managed goodness and power that SageMaker brings for model training, tuning, and inference in your own Kubernetes cluster without having to manage the underlying nodes. You can use this then to create repeatable pipelines. So treat the SageMaker operators as a primitive and abstract on top of them. So you could directly interact using Kubernetes APIs or command line tools such as kubectl, or you could build web UIs and dashboards and allow your data scientists to interact with SageMaker using the interface of your choice. And under the hood, everything is being orchestrated in Kubernetes using these SageMaker operators. And in a few moments, Ketan is going to talk to you about how Lyft, using its Flight open source platform, is doing just that. So how does this actually work? Well, David showed you a Kubernetes architecture diagram right now, and it's actually exactly the same. You create this YAML configuration file, and that uses the operators where you specify what type of job you want to run. You give it your training code. You tell where your data is stored, where you would like your model artifact, if you're doing training, to get stored. And it sends this to the Kubernetes API server, which then orchestrates the job in SageMaker. Now, what's really powerful about this is the way you interact with this job is native. It's as if everything was running locally in your Kubernetes cluster. So if you used, let's say, a TensorFlow job operator, and you're used to doing kubectl get describe logs, all of those core actions will work here as well. The logs would come streaming from SageMaker in your command line interface, and you can then interact with that job just as you would if it were running locally in your Kubernetes cluster. So we really worked hard to give this a native experience so that you can enjoy all the benefits of a fully managed service without having to change the way you orchestrate from Kubernetes. Last thing I want to mention here is we also added support for Helm charts. A lot of our customers told us that they've started using Helm as a way to manage various pieces within their Kubernetes cluster, and they found that sometimes these YAML configuration files can get complex for a lot of data scientists or developers who are less familiar with Kubernetes. And so Helm charts give you a way to create these jobs and interact with them without necessarily going in and creating these low-level YAML config files. So we support Helm charts, and we give you 2 different ways in which you can construct your jobs. Now, in addition to this, if you don't want to directly interact with Kubernetes APIs and the kubectl interface, the platform and infrastructure teams at your companies can build abstractions on top of this. So they can use the SageMaker operators as a primitive, and then they can integrate that into any platform they're using as long as it's based on Kubernetes. So bringing it all together, how does this look for an organization? And this is really where I think Ketan will be able to shed a lot of light on how this works at Lyft. But the way we look at this is Kubernetes gives you really powerful ways for orchestration. You can set up these repeatable pipelines, use us as a primitive, and now you can have the same standardized interface to build applications, set up pipelines that you were using previously. But that low-level management of the underlying infrastructure nodes goes away, because now that heavy lifting is being taken care of by Amazon SageMaker, where you can do the hyperparameter optimization, you can do distributed training, you can train and spot instances, you can create endpoints for real-time inference or do batch inference. All of that functionality, all of that fully managed infrastructure is now available to you from your Kubernetes environments. And so with that, let me hand it over to Ketan, and he can tell you more about how Lyft is using this with Flight.
Hello, good evening. Somehow I get the last slots in every conference that I go to. But hopefully everybody's caffeinated and want to hear about what I have to share today. But before that, I'll tell you a little bit of a story. I was leading a team at Lyft in 2016, before SageMaker and a lot of the other technologies existed. And we wanted to develop complex large-scale ML models and deliver them continuously in production. For example, if you open up an app, Lyft app, and you say, I want a car, how many machine learning models are being run over there? There are like actually 30 or 40 of them at that point itself. So Lyft prides itself being a machine learning first company. We have a lot of data scientists, a lot of machine learning engineers in the company. And we wanted to build stuff. We wanted to constantly deliver value for our users. So in 2016, as I'll continue with the story, is that I used to lead the team. I used to manage a lot of these machine learning engineers, and we wanted to continuously deliver value. The hardest thing that I always found was infrastructure. It was like the VP of product would come in and say, hey, I want to deliver this value. It's like, hold on, it'll take me 3 months to build this infrastructure, and then I'm going to deliver the product. And oh, by the way, by that time, the quarter's gone. So to achieve this, we started thinking about how do we really bring everything together and build the infrastructure that can power all of our needs now and in the future. Moreover, what we realized while we were doing that is that most of the data and machine learning systems are converging. Like if you read about machine learning online, or as David said, most of the people think machine learning as being the machine learning model. But it's more than that. It's like usually the data processing that happens, and usually many times cataloging of that data and making sure that you are able to reproduce all of these models that happen. And I'll give you a story about that too. There was a engineer in my team. He built an amazing model, and that actually served our ETAs for a while, and he left the team. And when he left the team, the model was on his laptop. It probably got destroyed or incinerated, and we lost the model. And then we had to rebuild the model. We were not able to rebuild the model for a month. And that's wasted effort in terms of cost, time. And the accuracy of that model after all of that stuff was not high enough. So it took time. And after that point, we resolved, never again will we have this problem, right? And this is early days. We were a small company. We are bigger now. So we started building. And we realized that we want a single tool that manages data, makes it easy for users, and tracks everything. Now, where does machine learning come into picture at Lyft? As I just said, that there are so many models. This slide actually shows a picture of a small subsection of various processes at Lyft that interact with each other. And if you look at those boxes, there's like ETA, there's autonomous, there's hybrid maps, all of them. Many of them are individually machine learning processes. And these boxes themselves are arbitrarily complex. Right? Inside them, you would see intricate dependencies and data flow that's happening in each of these boxes, because actually each of these boxes is a team at the company. But not everybody always is building machine learning models. They're many times building data that actually supports a machine learning model downstream. And an interesting fact over here, all of these flows are powered by Flight at Lyft. Flight is an open source framework, and I'll quickly introduce it in a little bit. Currently, it has about 400 daily active users at Lyft. It's running more than 3,500, probably about more than 5,000 workflows uniquely, constantly. It does millions of container executions, and it does all of this natively on Kubernetes. But when we were working with all of our customers, so I lead the team, and it's like a platform team within the company. So we have customers. All of the daily active users that I just talked about are our customers. And when we were working with our customers, we realized that there are many important things that you need in a machine learning system. And two of the most important ones that we figured out, we wanted to attack first. And one of them is we wanted to orchestrate machine learning and data workflows. So provide a way to generate data deterministically, repeatedly, and durably, and then feed them into machine learning models, and probably take that and predict. And all of this is a pipeline. So we wanted this to be absolutely scalable and painless. We also wanted to enable collaboration within the company. So there is an expert who knows how to build a deep learning model. Not everybody needs to be a deep learning expert. He's built a model. Let's use that model. Or if there is an expert who knows how to process the data, right? Data processing is very hard and very important. He's a Spark expert. He built some Spark process that actually takes our ride information and does it, chops it in a way that it's useful to build certain models. Let's reuse that process. So to do that, we actually, and I think commonly this is called as MLOps in the world now. We wanted to make sure that we are able to collaborate, reuse, and perform MLOps effectively within the company. So with this, I'll introduce Flight. It's an open source platform available on flight.org, as I said. Some of the tenets of this platform was that we wanted it to be like an AWS service, a hosted, scalable, and serverless orchestration platform. Our users just purely think about business logic. They write code in the language of their choice, ideally, most importantly in Python, and then they do not worry about the scaling and resource pooling and quotas and all of that stuff. It just works. It's a fabric that connects disparate compute technologies. So when I bring data back into the picture, along with ML, there are many technologies. Spark does a great job at certain things. Hive does a great job at certain other things. Presto does a great job at some other things. Along with that, TensorFlow and PyTorch do a great job at training models, and XGBoost does a great job at training models. So we wanted it to connect all of these different hybrid technologies. We wanted it to be extensible and observable. Extensible because as we were working with these teams, we had a version V1 internally. What you see outside is V2. V1 suffered from lack of extensibility. And that actually frustrates all of our users. They're like, no, I want to add this feature. And we're like, why? It'll take 6 months. They're like, nope, that's not good enough. You were ending up in the same thing that we initially started off with, that there's a lead time. So we wanted to get rid of that lead time. We wanted to see if we can really accelerate extensibility within the system. So extensibility is a very top-level primitive within the system. We also did not want to reinvent the wheel. If there is a TF TensorFlow operator available outside that does a great job of running distributed TensorFlow jobs, then we should use that. If SageMaker does a great job at some things, we should use that. We basically wanted to use the best of the breed that's out there and only innovate where innovation is required. And along with all of this, of course, we didn't want to have somebody leave the company and us lose the model again. So of course, we needed it to be auditable, repeatable, and secure. Security is another thing that's like with all the data privacy stuff, we wanted it to be secure at the platform layer. So how do we do this? I have actually removed some of the code slides from here, but we'll look at the code in the demo. So to understand how flight works, we have to understand two primitives in the system. One of the primitives is called a task. A task is the atomic unit of execution. For example, it could be a Spark job. It could be a Hive query. It could be a model training job. And so tasks can be arbitrarily complex. They can be, as I said, Spark, Hive, or a training job, or simple Python function. And they are strongly versioned and always declared using protobuf in the system. When you have multiple tasks, so in the diagram, actually, if you see, there's a Spark task on the left, there's a Python task on the right, and they feed into some C++. Actually, we run code in C++ for autonomous. Model training happens in C++, which is quite different from what many people think in the world. The reason why we wanted, sorry, I forgot to add one more thing. Tasks have an interface. That's how you define a task. A task has a set of inputs and a set of outputs. And it's like any function that you write in any programming language. The reason why that's important is because when you chain together multiple tasks, you get implicit compilation. That means only a function can be chained together with B, with C, with D. And Flight does that for you. And to do that, you have to, of course, declare the interfaces for those tasks and then chain them together. Once you chain them together, those are called as workflows in the system. And workflows themselves have interfaces. They have inputs, they have outputs. They are like these meta functions that are declared purely in specification. And we'll see an example in a little bit. And putting it all together, this makes a pipeline in the system, or what we call it as workflows. Now, we also wanted it to be, as I said, serverless for the users. What does that really mean? I said we wanted users to purely focus on business logic. Like on the right-hand side, there's a function which is written in Python. Users can just purely say, I want GPUs, one GPU, one CPU, 400 gigabytes of RAM. 400 is too much, but you could. People ask for that. And it should just magically appear. Same thing. If you are using some service like SageMaker or your internal Hive cluster or whatever, that has limitations. It cannot do a million queries per second. So you want to do resource pooling and resource isolation for all of them. So we wanted to provide that easily. We also wanted to make sure that when two users come and both of them are in the immediate need today to solve their model, which always is invariably the case, it's end of the quarter, 1 week to go, I want to build model and deliver value today. We wanted it to scale automatically, just effortlessly behind the scenes. Also, not affect each other when a third user comes along. That's important. So fairness is required. And along with this, we wanted all of this to be available as a service behind a REST and a gRPC interface so that you can integrate and interact with it in different ways. The way we did it is, this is our architecture. The serverless portion's powered by Kubernetes. Kubernetes makes it easy to run containers. But it's very hard for data scientists or machine learning engineers to write YAMLs. And it's interesting that we are expecting them to write YAMLs to run things. What we do is essentially write code in a TSL, like Python, and we convert it to the right set of YAMLs or whatever we need to, and then run them. And the way we do it is on the left-hand side. Flight is a very classical architecture. It consists of a user plane. The users that sit and they interact with the system use any bits in the user plane. So in this example, Flight CLI, Flight Kit, Flight SDK are user plane components. They use that to talk to our control plane. A control plane is a service that is hosted, available at a well-known endpoint within the company. And you talk to it, and you request various actions from it. From it, you can also observe everything using a console, which is also a hosted, well-known endpoint within the company. Once you use those two things, you create a workflow, and you execute the workflow. The execution actually happens by this thing called a flight propeller, which is an extension, just like Aditya said, an extension of Kubernetes. It knows how to run pipelines. And it's specialized in running pipelines. It runs pipelines, and it works with other operators and other Kubernetes primitives to achieve the desired result. And we'll see how that magic works. But like most of you, when we start off with, one Kubernetes cluster will be enough. But as I said, we were running millions and millions of containers. One Kubernetes cluster is not enough. So we quickly had to move at Lyft to more than 10 Kubernetes clusters. And all of that is backed behind one simple interface. The complications of the cluster, migrations, deletes, which cluster gets what. And let's say there is a big user within your company who wants to use the entire cluster. We just direct all that traffic to their one cluster. All of that is called as MultiCluster within Flight. And it's available out of the box because we built it for Lyft. Now everybody can get it. But to achieve the multi-tenancy, we had to build in some primitives within the system. One of them is a project. Think about project as a team in the company or an initiative that you're trying to solve. So I want to build ETA for my customers, and I want them to be, and I want a bunch of machine learning models that solve that one problem. I will group all of them together under one project. And within the project, you can have multiple domains so that you can get CI/CD like semantics to your pipelines. For example, there are some systems out there where you can just deploy a pipeline and the production pipeline breaks. We didn't want to do that. Everything's versioned, and everything also goes through a nice CI/CD process. So you deploy it to development first, then you go to staging, then you go to production. And it's configurable. You want two environments, you can have two environments. The last thing is, when you run this platform at scale, you realize the biggest thing becomes the cost. And so we wanted constant billing and understanding of who's spending how much, which team is spending how much, why was that spend happen, what is the ROI on it, which is actually outside of the platform, but that has to be calculated. Because machine learning oftentimes is an expensive operation, and then you need to know whether it really resulted in an output. All right, that's improving your bottom line. So that's how Flight allows you to track the spend that is done per project, per domain. And I briefly, I talked about that we wanted it to be shareable. This is how it's done. On the left-hand side, let's assume there is a project A. Some team A built a pipeline, and it also built a model. Some team B now wants to use that pipeline, extend its capabilities, add its own set of functions, and also add a new model, or use the same model and massage the data that was output of pipeline A, and you pass it to the model. You can, like as if it's a dependency of a code, you can simply invoke it in your code, as you see on the right-hand side. So right-hand side, you'll see the first step is actually a composition of another pipeline, and that composition is loosely coupled using the actual place where you get it from. And once you hand it over to the Flight system, Flight sees, you actually want to use that pipeline. I'm going to pull that pipeline out. I'm going to try and put it into your pipeline and see that whether the inputs and outputs match. And once the inputs and outputs match, it says, yep, it's ready to go. You can ship it. And that's great because you won't get runtime failures if the inputs and outputs match. But to also achieve some of these crazy things that we wanted to do, we had to build another interesting system. We called it as data catalog. So let's take an example first, and then we'll talk about what it is. On the right-hand side, there's a workflow W1, which triggers two other workflows, W2 and W3. You start W1, it could be an ETL process, it could be a machine learning process, and workflow 2 succeeds fine, everything's awesome. You probably spent $1 million building all of this, but workflow 3 failed. And it failed at one of the last steps. And why did it fail? Oh, we were typecasting an integer to a string in Python. If you have done Python, you are aware of this problem. And so how do you solve that problem? You go and fix that code. But when you deploy, what is the next step the user is supposed to do? Is he supposed to run that task itself? Does it run well in isolation? What if it had further downstream dependencies? Or is he supposed to trigger W1 again and incur the cost again? So what we do is, if you say so, we mark every task with a special signature. And once we recur that signature anywhere in the system, we substitute the outputs directly. And that's called as memorization. It's very useful in machine learning, because what will happen is the data processing steps might be very expensive, but the training steps might be very cheap, but may be error prone. So you might have to rerun them again and again. So in this case, you just rerun W1. And what Flight will realize is that W2 is already done, so it's not going to incur any cost. It'll only run W3's task H. And then once that completes, W1 will be marked as success and move on. But this also has another side effect. We get a nice causal dependency graph amongst all the data that is generated within the company. So task A generated something, task C consumed it, and so W2 also consumed it. And you can store all of this graph structure somewhere and make sense of it. Like, this data is very useful because it's used by so many people. There was a bug in this data set, so let me build all these downstream models because there are repercussions now downstream. But again, as I said, I manage a platform. So running a platform means there are a lot of operations. So we wanted to make it really easy to manage a platform at this scale. We wanted to do it on both fronts, make it really easy for the users so that they don't come and ask us the same questions. So Flight comes with very deep visibility into, oh, here are my pipelines, how many are failing in the last 1 hour, are they succeeding, how much time did it take, how much cost did it take, and so on. We also have deep platform level visibility so that I can manage it easily. We also come with, it's directly integrated with PagerDuty, Slack, and email notification. So you can just annotate your workflow saying, hey, whenever this succeeds, send me an email. Whenever it fails, send me a PagerDuty, and it'll do that. And coming soon, we are actually using the same mechanism to give out subscribable, programmatically subscribable notifications so that you can actually take actions and react to those events rather than like waiting for something to happen, looking for it, and doing stuff. Security also needed, as I said, briefly touched on it. Security is very important. We use OAuth2 to model the security. And all the executions have a unique role associated with them. So on AWS, that would look like every execution has an IAM role associated with it. So 2 executions running on the same platform cannot access the same set of resources. They have to provision it through an IAM role. The last bit, as I said, was extensibility is a core primitive within the platform. How do we do that? Flight is extensible at all layers. And there are 3 planes. We talked about the control and the data plane and the user plane. You can easily extend Flight. The easiest way to extend Flight, rather, is in the user plane. You do some stuff within your container. You make it easier for you to use something. And for Flight, it's opaque. But you can rapidly add new functionality. For example, in Python, if you're using our Python SDK, you could implement, if you're aware of Airflow, a sensor task that waits for data to be generated in some S3 file. Or you could launch a SageMaker job directly from Python. And as long as you have the right IAM roles, you will be able to do that. It should be fine. But there are problems with it. And few problems are that it's opaque to the Flight platform. So Flight platform really cannot help you in case of problems. It cannot really show you what's happening inside that container. Neither can it show you, in case, let's say, a user goes and stops the execution of the $1 million job. It has started a SageMaker job. It will not cascade the stopping thing to the actual SageMaker job. So your container will die. Flight will think, awesome, this is gone. But actually, the job continues to run and cost you money. So to do that, Flight's backend is itself extensible. And that's what we will be using today to show how we extended the Flight backend to work with SageMaker Operators and improve the backend itself. We have various ways of improving the backend. You can actually call services directly. It's a little more work. Or you can use Kubernetes operators. If you use Kubernetes operators, we have created a special interface that makes it really trivial to add new extensions into Flight. So for example, adding that TF operator, or somebody actually in the community is now working on a Dask operator, or there's a SageMaker operator. It becomes trivial to add it. With that, you get customized visualization, and we'll see in the demo, like logging, directly showing the logging or the progress information or whatever in the UI. And this is perfect for managing CRDs. Now, all of this leads to like, why are we looking at SageMaker? So Flight, as I said, we are not the people in the company who choose the platform for you. We say, here are all the options available. You make the choice. And after we figure out what's the right thing, we probably cut it down. Our aim is to provide all the best of the breed things that are out there to our users. And to do that, we have to manage all that infrastructure. It's hard sometimes. So we looked at SageMaker. We're like, it fits the bill in many cases. It offers us many functionalities that we miss. But it also gives us an option to maybe build certain things as we want, where we want to differentiate in the future. But use SageMaker for the things that they're perfectly working fine. So it's a good mix of when to use a managed service versus when to use our own service, or when to build and when to buy. Right? It allows us to do that amazingly well. So we looked at SageMaker, and we said, like, OK, and SageMaker Operators was amazing. Made it really easy to add it into the system. So this is how the flow would look. A user basically writes some code in their Python. It's in the same exact way how they have been writing for all their pipelines. And it gets handed over back to our engine. And the engine has the special plugin layer that we've written, which calls the operator, and the operator does the rest. It actually goes and runs a job in SageMaker and returns the results back. And all of this is completely hidden from the user. The user thinks he's using the Flight platform. And at the back, we may show that it's actually a SageMaker job. But if we switch it out in some cases to something else, that's perfectly fine. Or if we think that today, whatever you're using, we replace it with SageMaker, that's also perfectly fine. And the most important thing, writing code is still simple. You still write simple Python code. There's no YAML. There is nothing new to learn. There is a nice interface that comes with documentation. You write those 4 things, and it starts working. Let's do the demo then. So in the demo, we'll see how actually the workflows are created and the UI, and how SageMaker makes it really simple to perform a relatively complex task. And then we'll, if possible, we'll talk about data catalog and memorization. Actually, before I
can just switch over.
I might have. Oh, I can just switch.
It's already connected.
Is it switched?
Yep, you're on the screen.
Oh, cool. So that's our UI. It's updated a little bit, but this is from a beta sandbox deployment that we have right now. So if you quickly see, what you see over here is the projects. These are human readable names for projects. So I created a project called Flight AWS Reinvent, completely isolated from every other project within the company. And these are the various domains. And just to prove that we can add arbitrary number of domains, there's a domain called as a domain, popularly called as environments. We also have a project called as AWS. Let's just jump into it. This is the UI. It shows workflows. There are other bits getting added. But if you go and look at it, the UI quickly, I don't know if I can drag it, but if you can see this, it's actually showing a Python error message directly in the UI. So what happened is the pipeline failed at some point, and we were able to capture the output, the error, and directly show it in the UI. And this pipeline is essentially trying to do split and fit and do some predictions at some point, and this is the error that we got. Every step, as I said, or the pipeline itself has inputs. And you can see the inputs. It did not produce any output because it failed. But every step, let's look at a successful step, has inputs too, and it produces outputs. Right? And we'll talk more about like these special type of outputs. And the task itself is a pure specification underneath. So you can write it in any language, trust me. And there are people writing in C++, as I said. The task has one of the most important things is the interface. It has a set of inputs and a set of outputs. And the outputs are very declarative. In this case, they are this thing called as a schema. And we'll look at it in a bit. When the execution progresses, let's go back to some other examples. For example, this one. When the execution progresses, it also creates a link to the graph, to the logs. In this case, this is a cached example. So it creates a link to the inputs, outputs, and task. And of course, there is a link to the logs, which I'm missing in a live demo always somewhere. Yeah, there you go. So you have links to the logs for that task specifically. And for the example, so this is our quick UI. Of course, you can, for a workflow, you can do a launch. Because we understand all the types, we automatically generate a launch form for you, saying that, oh, you need to provide a data set, which is a link, and a float value called the split ratio, and the seed integer, and hit launch. And that's about it. It should start running. Now let's look at the example that we are going to work on at the moment. So in this case, there's a popular data set available online on UCI. So we're going to use this data set. It's a diabetes prediction data set. It's predicting whether somebody has diabetes given some set of parameters. The interesting part, the reason why I chose this data set is because it is a very structured data set. It represents real-world data. Real-world data is usually structured, right? There are non-structured data sets, which we also have, like LiDAR data sets and images and whatever, which is the most common thing that you see outside that machine learning is talked about, images and things like that. But many real-world things use structured data, which you get from Hive or Presto or whatever. In this case, the structured data has a set of columns. And those columns are called something. And each of them have a type. I don't know if you can, maybe I should zoom. Each of them have a type. Like in this case, it's an integer or a float or whatever. And Flight allows you to represent this data set as it exists in real world. Let's run it, then you can go in and actually write a function as a task. In this case, it's a simple Python function. It takes in the data set. It also takes the classes that you want to, it's a classifier model that I want to train. So it takes a bunch of features and the actual classified values to train a model. And in this case, I'm training a XGBoost classifier. Really straightforward. I do a fit, and I produce the model as a pickle, and I produce that as an output. So that's once you have the model, you can put it together into a workflow. And a workflow here also consists of inputs. So in this case, the data set and any other criterion. Like I may want to split the input data set into two parts of validation and training data sets in some different ratios. So it's taken as an input. Then we take the split, the fit task, the predicted, and the score task. The score task are the set of tasks that it runs. And it produces some output. And the output consists of the model and the accuracy. So let's run this. To run this, we'll have to register the workflow. And we'll talk about what registration really means. Because we are completely versioned, whenever a user creates a new workflow, they register it with the system. And the registration records all the versions that are getting registered with the system. So you can now go back in time. You can run any old model or any new model. And so if somebody leaves the company, you can always go and rerun it. Actually, I was running the advanced model here. I'm going to go back and run the subtle model that we just talked about. OK, so let's register it. So that's going to create a version plan. And we are going to launch it. And that launched a run. Let's open the launch. And so it's running. It's actually already complete. And if I refresh it potentially, it shows the time is 3 seconds. It took 3 seconds to complete this huge graph. We'll see why in a little bit. And then I went ahead. It ran again. You should never do that with Jupyter. It runs the same thing again. But because I was caching, it went through again quickly. So now we are here. It produced the model. Sorry, let's load the model. And the model accuracy is 63%. So if we can go to the UI also, we can see the same. So the inputs were this. The output was the model accuracy, which is 63% in this case. And let's use this model for some prediction. So to do that, you have to download the model. So now in the same notebook, you can download the model from our APIs. Boom, the model is downloaded. And let's predict. Oh, this guy has diabetes, and this is a likelihood of 83%. Again, why did all of this run so fast? We'll get there. But we are here to talk about SageMaker and how can I improve this process further? So what we saw is a simple XGBoost model that got trained, but it got trained with these things called as static hyperparameters. Hyperparameters are certain parameters that are orthogonal to the data in the model. For example, XGBoost model is a type of a tree, so you can have a different sets of hyperparameters for it. For example, you could say that the depth of the tree should be no more than 4. And what that would do is limit your model to not have depth more than 4. But you could also say the span of the tree should be X, or some other sets of, like, when you're training, use these many number of threads or these many epochs or something, right? And that is usually, nobody really knows the right set of those values. So the way to optimize them is this thing called as hyperparameter optimization. Or in simple layman terms, you throw a bunch of things on the wall and see which one is best and pick that one. But that's expensive. And that's hard to write, because you'll have to run a lot of things in parallel, sync the values, and again rerun. But with SageMaker, it's really easy to do. So what we're going to do is use the new thing that we developed. It's a SageMaker plugin. It looks exactly the same. It's an XGBoost training task. But XGBoost, also the other thing to understand over here, is a black box model. The code doesn't really change for the model, right? It's always the same model. You pass the data to it. The code doesn't change. It generates a model output. So what we have done is we have actually hidden XGBoost from everybody. You just provide a bunch of data as the input and the set of hyperparameters, and it'll train that XGBoost model and return the model. And but we couldn't just directly use SageMaker, because the data set, as I showed you, is a structured data set. And in such case, SageMaker wants the data to be oriented in a specific way. It wants the output labels to be the first column, and all the other features to be the second, third, fourth, and so on columns. While the actual data set in the real world is oriented in the opposite way. The first few columns are the feature columns, and the last column is the classes. So what I have done is I actually wrote like a workflow. I took the data set as a structure, and I reoriented the data set. And that's what I called as the transform task. Then I called the XG trainer, and SageMaker also returns the tar as that model as a tarred file. For my demo, I wanted it to be an untarred file, so I used that in the same pipeline. I actually untarred it. So let's register that thing. But hold on. Let's not run it here. Let's do something fun. Let's go back to our old notebook that we were working on, and simply go and replace the fit task in this case with the XGBoost hyperparameter optimization fit task. Why does this work? Because we have the same set of inputs and outputs, because remember, I massaged the data and I created the outputs to match. Now the interface to this higher level pipeline is the same as my previous fit tasks interface. So I could just replace the thing with a fit task from SageMaker XGBoost Hyperparameter Optimizer. Let's register it, and this time let's register it as a different name. We can register it in the same name. It creates complications to look at it, so let's register it in a different name. The only difference is there's an underscore HPO in the end. Okay, so let's register it. It registered. Let's run it, and let's see what's happening. There's a slight difference. Now you see this fit task is getting run. Fit task is actually a nested task, which has a bunch of steps. What's happened is actually it's run a completely separate workflow that does a bunch of transforms, and it does the training set, and the training produces a model. If you, again, 2 seconds, wow, go back. I'm going to run out of battery. Hopefully not. So this will complete, but let me first find some. Can I use this one? Okay. So while we were waiting, it completed in 36 seconds. And the input and output are the same. The inputs are the same set of data, and the output produced a model. This time with 66% accuracy. We didn't do anything. We really just switched out and used a hyperparameter optimizer with static hyperparameter values. I didn't even tweak the hyperparameters. So if we go down and like just load the model, it'll again say, yeah, it's 66% accuracy. Let's try and see if the model gets loaded. Should get loaded because of the type safety. And now when you're back in the pandas data frame, it actually predicted the same class 1, but this time with 86% confidence interval, so it's actually better, right? So, so that's integrating with SageMaker Operator. In the backend, though, what was happening? Why did it run so fast? Remember the memorization stuff that I talked about? Preparing for the demo, I ran this model a bunch of times, of course. And when I was running it, so let's look at the hyperparameter optimizer. When I was running it, if you I think the screen is a little on the right-hand side, there is no way to alter it. But if on the right-hand side, if you look at the times, there's one that is 11 minutes long. And everything else after that is 36 seconds long. What's happening is it sees that, oh, I'm relaunching the same model or the model training with the same set of inputs without even changing the split ratio. If I change the split ratio, we'll see that it'll start running because it's like, oh, this guy wants to do something different. Otherwise, it's saying that you're running the same thing. I'm just going to reproduce the same output for you. And it can do it partially for some steps too. And in this case, if you go back, actually go in, it's run some of the steps for a longer time. And if you actually split, it ran for no time, almost like 3 seconds or 6 seconds maybe. And the reason why is because it was memoized. Only one step was memoized. And the fit task is a workflow. Let's look at that workflow. It ran the train node, in this case, for 6 minutes. And because it's a backend plugin, we can show richer integration, like directly jump to the SageMaker job and show that how it's running. And it's like, oh, it completed, and each one, it ran like 9 steps of multiple optimization, distributed optimization. It also shows logs right in line over here. And you can like browse through and see like how it was optimizing for that. And these were the hyperparameters that it was using. Almost wrapping up. We talked about everything, so let's make sure that I have covered everything. If not, can we go to the other? Can we switch the laptops? I don't know. How do I switch the laptops?
Can we switch back, please?
Okay. Yeah, but the demo summary is that we learned how to write a workflow. We learned how to write tasks. We looked at the accuracy of the model. The accuracy of the model improved just by hyperparameter optimization. And it was really simple to do that. And we were able to see the logs. We were able to see the execution and memorization. That made it really blazing fast. We could rerun it, and it'll run in 3 seconds. Thank you.
Awesome. So just to quickly wrap things up, the really powerful thing for me in this demo that I took away from what Ketan showed us is we've now found a way to bring SageMaker into your own custom Kubernetes platform. Right? Kubernetes is a platform for building platforms. And as we give you these primitives, you can choose what is the most powerful and flexible way in which you can integrate this to get all the benefits of fully managed model training, tuning, and inference. So with that, we can end the session. Thank you so much for being here. We're happy to take questions if you could come up to the mic. And we'll be around afterwards for chatting as well. Thanks so much.
Yeah.